Okay. So I'm Danny, and I know a lot of you folks. We're going to be talking today. This is actually a follow-up panel to a panel that Dave Ward hosted in Oakland at NANOG something or another about 3 back, and Dave's panel gave a service provider perspective, and this is actually just meant to give a vendor perspective of where things are going and what vendors in the core space see as important, and if service providers have feedback, then I'm certainly open to that. So, all right. So the panel members are Dave O'Leary, Dave Ward from Cisco, Eric Brendel, who's standing in for Kerry Parker from KRO Networks, Oria Roos on the end down there from Charlotte's Web Networks, Pune Agarwal, okay, I butchered the name, Riyadh Hartani from Caspian Networks, and Scott Perezzi from Avicii Systems. So I have an agenda. Let's just skip by that since we're already off. We'll try and make sure we're done by 11:30, I think it was, or 10:45. Okay, and then, so I've already said most of this. I gave a list of topics to the panel members when I invited them and said, these are the things you can talk about, and try not to put too much marketing stuff in there, that kind of thing. And, 5 to 7 slides, whatever. They had 10 minutes. Some provided more slides and actually promised me they'd talk fast. So I'd intended to reformat the slides so that they weren't so, busy, but it was a lot of work, so I decided not to. And we're actually going to go to Dave Ward's Dave Ward first instead of Dave O'Leary. So with no further ado, David, if you want to come on up.
Thanks, Tim. Good morning. So I'm back again. I think this is a few NANOGs in a row that I've been up at the mic, and this time on this panel, as Danny mentioned, I'll be talking about building core networks and core routers in the 2002 economy. What's kind of interesting is I hope to use, and I will directly use some of the data that was presented in Oakland to back up some of my claims. So I'm going to be I'll be one of the fast talkers, I think, this morning. What you see on this particular slide is really from a Cisco perspective and from my perspective, where we are within backbone growth and what we're seeing as the predominant links. And what you can see right now is we are still firmly within the core service provider market, still firmly within the OC 192 backbone build-out. Actually, a lot of networks are in 48 or potentially even building smaller core links, but really 192 is the sweet spot for the build-out, as we can see from our customers and requirements. Now, what you see up and to the right, of course, is heading towards 40 gig backbones, but that's not exactly what we're seeing as the predominant build-out today. Also, in internet architecture evolution, really where we are in 2002 is, again, IP at 10 gig, the sweet spot that we can build both optical and IP networks, and the sweet spot for having us build them for long-haul, ultra-long-haul networks and begin to overlay IP and optical services and integrate them together. IP has been dominating clearly as the backbone transport packet format for several years now. ATM, as Ted Seeley mentioned back in Oakland, is dead, and IP is reigning king in the core. So this is taken directly from a customer who I think is here today, who might want to sing the song that goes with this, but really the point of this is that building core networks and building core routers requires VPN support, requirement for small boxes, small volume inside a POP, because we have to deal with legacy POPs, can't build out new POPs, the economy is that way. We need low power and HVAC because we all hit those requirements. The transition from 10 to 40 gig, have to have improved performance, of course, and throughput on each card for line rate, easy to manage, all the features, low prices, high availability, quality of service, and of course, you want it before we could possibly finish it, and yesterday would be better. The whole thing has to be flexible. It's got to be done fast. All the vendors, I think, on this panel are probably panicking. If they haven't, we should be. And basically, my response is, what else could there possibly be at this particular point? Because that seems to be just about everything. So what we learned when building core networks from the panelists that we had in Oakland was that In the old days, building core networks, was, basically hook up the routers with a fully meshed network with some redundant links, and there you go. Basically, a generic backbone as presented by Ted was POPs interconnected with the solid lines as being the primary links and the dashed lines as the redundant links in case there's a failover. The POPs, once again, interconnected POP to POP as well as across the WAN. And really what it would look like was a hierarchy something akin to this, where you had in the old days, 48 OC3s going up to 48. And again, you can see the point of policy that would be applied, and that what we're doing in this particular case is burning a lot of interconnect ports on the line cards to make sure we have a highly available network in case one node went down or one link went down. Now what was realized, I guess, back in 97, 98 now, was that when you build a network like this and you have these fully connected links, you end up, or your IGP ends up, building metrics such that one link is going to carry most of the traffic going from a router to router across the WAN. And so traffic engineering and MPLS was, in those days, one of the reasons why it was invented was to be able to overcome the IGP metric and utilize to an improved degree which links you could send traffic over, and trying to turn them all up because they're very expensive. Now what we've learned since then is, in fact, we can build technologies that allow us to burn fewer ports and allow us to have the high availability we need inside the network for both node and link recovery by building rings within metro areas and within POPs and across the WAN as well. And the point of policy is still roughly the same that we learned in Oakland, which is basically at the edge, the further to the edge that you can push your policy for QoS or traffic engineering or VPNs, the more likely you're going to be to be able to handle your customers' needs and requirements. But what we also see is that points of policy need to be applied where we begin to have core aggregation, and that presents a bit of difficulty for us, the router vendors, because really what we end up running into is building boxes that end up having to serve many, many needs. The other thing that we see here is when building these metro and core rings is that we can begin to reduce the meshy nature of the POP interconnect and begin to cut down the n squared problem of the number of ports that we're actually burning, and begin to use the density that's becoming available on high-end routers. So what Ted presented was this particular chart back in Oakland, which showed from Sprint's perspective how to build for a WAN core at 10 gig and how to interconnect data centers, customer peering, content that they have, and how to build out their metro and regional areas using SRP or DPT rings. So what becomes challenging, though, from the point of policy and the application of policy out towards the edge, is that we end up having to build devices that, again, have multiple tables, can handle multiple topologies, multiple overlay networks, multiple address families, multiple logical routers. And as these are connected into one device, and as customers are connected to these, what we end up running into is building a lot of boxes that have a lot of the same features, which is quite challenging. So the question really becomes, from a vendor perspective, can one router, can all of these functions collapse potentially down into one large multi-chassis router, or can they be collapsed into one chipset that can be reused so we have end-to-end feature set? Can they be collapsed into one software base such that we know exactly what features are in there and we can manage this more effectively so you can manage your networks more effectively? And in fact, the big question that's coming out of this and that came out of Oakland is what can be converged out of all of these different aspects of building a router and building networks? So there's some conflicts here, of course, and the conflicts with these goals and when attempting to build devices both at the edge and the core is that we aren't talking about dumb packet pushers. And we have this trade-off that we've been talking about for years and years and years, and it's still overheard in hallways and in bar rooms, which is that, well, hey, all routers do is make a forwarding decision, update a header, forward the packets to the correct outgoing interface. What's so hard about this? Well, perhaps back in 1994, that's all routers were doing, but here we are today where we have some of these newer features, and we're running a lot of them today: multicast, V6, diffserv, different priorities, weighted for queuing, the latency requirements that Ron, Ted, and Sean mentioned back in Oakland, packet sequencing issues that have run into drop policies, VPNs, etc. This is in direct conflict to building dumb, cheap packet pushers, because what we need to be able to do is consolidate what we can boxes, chipsets, software, et cetera, in devices, and trade this off versus the features and where they need to be applied in the network to, again, help build end-to-end networks that actually can provide all of these services to you and to your customers. So software on the router, back to the dumb packet pusher model, used to do three things. So the three things that software does in a router: forwards packets, puts them in the correct direction, which is all about routing, and it makes it easy for the operator to engineer traffic, and that used to be a CLI. Well, these days are pretty much gone as well for software, because we have tens of treatments we need to do to forward packets, to pull stats, V4 unicast, multicast, V6 unicast, multicast, MPLS, tunnels, optical control, traffic engineering. It no longer is just update the header and pass on the packet. We have to be able to route, but there's also requirements that have been given to us for selectable algorithms depending on topology, adjacency, and level policy searches that are required now to administer networks, and of course converged instantaneously, so that way we can build VoIP networks or voice over IP networks across LAN backbones. End-to-end manageability solutions, it's no longer just a CLI, right? CLI has to be there, but we need CLI with guru hooks, we need pointy-clicky interfaces, and of course there has to be infinite storage for collecting statistics and packet sniffing on these devices, making it a bit more challenging. Of course, I'm not just up here, whining that the requirements are too tough, we can't build these devices. We're all attempting to build these types of devices, and it all makes perfect sense why these requirements are coming to us. New regulations, security concerns, new different services, so that way you can make more money to get more customers and have different offerings between the different networks. Converging infrastructures, either collapse of overlay networks or convergence of overlay networks, converge of the services you want to provide in the edge and the core or at aggregation points, can no longer afford overlay deployment strategies, acquisitions and convergence of networks and service provider networks going on every day. Of course, requirements to reduce CapEx, OpEx, build better billing systems to generate and understand what type of revenue and revenue streams are possible from your networks. High availability, high availability, high availability again. In Miami, I gave a presentation on nonstop forwarding and routing protocols for link and node high availability, and I think we'll talk a bit more about this with the rest of the panel members. And of course, part of high availability is to increase uptime, because that is the chief differentiator you'll have, as has been told to me, between your competitors. But there's some difficulties when trying to build routers to these requirements. And on the hardware side, it's memory speed as well as CPU instruction cycles that are available. And on the software side, well, the software is the router. That's an old adage from another company I worked for at one time. To trade off features, high availability, number of lines of code, and be able to test this all out. And what becomes difficult, really difficult with the software, is that the software on a router now is an asynchronous distributed system, where each card is now doing independent processing, but it all needs to hang together as one unit in one unified router. And there's a bunch of cheeky catchphrases going on in computer science now, whether it's grid computing or cluster computing or potential some client server or peer-to-peer inside the device. That's really not what a router or networking device is. It is running as an asynchronous distributed system, more analogous to a supercomputer these days, thus providing the challenge. And of course, it's extremely specialized for network processing and routing convergence. So the lack of simplicity in network design due to the complex service offerings that you've told us you want to be able to provide leads to extremely complex devices. And back when first building routers in 1995, 1994, still the same focus on hardware that we had then that we have now, which is really on how to make lookup tables faster, how to make memory faster for buffer and state memory of packets, and how to make better schedulers. And the real issue comes down to memory speed and memory access once again, and the ability to buffer packets in memory using DRAM, SDRAM, RDRAM, and whatever technology is available to be able to handle this, because we're down to single nanoseconds when running at these types of speeds to be able to process packets, which isn't very much time to get in and out of memory or across. Oh, that does not look very good. But the memory bandwidth slide that would show that DRAM since 1981 has been able to have improvements of 1.1 times over 18 months versus Moore's law, which is 2 times over 18 months, and link capacity, which is expanding at 2 times every 7 months. So Houston, we have a problem with memory access. Packet processing, you see on this logarithmic scale, the number of CPU instructions we actually have to process packets has gone from upwards of 1,000 to downwards of about 10 as of last year to be able to process a packet at line rate. So we have challenges of CPU and we have challenges of memory bandwidth. And really what this comes to is my summary, which is these 2 hardware problems have been plaguing us building computers and building network devices, and so yes, in fact, we are channeling Seymour Cray back into the room, and I think Jeff Wabick back in '95 gave a similar talk channeling Seymour into the room, with the difficulties we have of how much power we can put into these CPUs, how much memory we can put in the box for cost, size, weight, power, heat, dissipation. These are all trade-offs that we have to make against the requirements that you've given us to be able to provide the services. Control plane complexities. The feature list is always getting longer and it's rapidly changing, but that's been the name of the game since I've been in it at least. Next bullet, which is kind of clear. The economy is hosed. Growth is slower. The speed of links and how fast we're going to 192 or 768 is slowing. But the number one thing that I wanted to get across in my few minutes here is that the big dumb core box isn't going to cut it, and I think everyone's pretty much going to present the same thing. You know, most core routers have become the new edge, or certainly have customer attachment where you want to provide these services. Even in the reduced mesh case, as I presented, I think in slide number 4, core routers need to have all the features because that is a point of policy that was mentioned to us by Ted back in Oakland. But of course, you know, to wrap it up, it never was easy to build a core router, just like it was never easy to build a network, and if it was, you know, history would be different than what it is today. Thank you very much.
I wanted to mention real quick that Susan put a PowerPoint file up, and so she has all the stuff on the web already, so thank you for that. And back now, Dave O'Leary is going to talk for us. Juniper Networks. Here we go. Thanks, Dave.
Okay, I think you probably see some common threads through a lot of the speakers here today. These are the topics that came up on our discussion, similar to the list that Danny had. Basically, quite a few things to talk about in 10 minutes, so again, I'll try to make it through pretty quickly. Tried to collapse some of them down, the related ones, into a smaller number of slides. So, reliability, availability, survivability are all related topics, certainly. I think the good news here is life is getting better. A few things, expectations have certainly increased in this area quite a bit from the days that Elise was talking about back when it was a challenge just to forward packets. And in accompanying those expectations have also come an increased willingness to invest in technology and mind share in developing the technology to improve our both the individual boxes, but also the network and the services that run over them. So this exhibits itself in a bunch of different areas: hardware, both through increased integration, you know, fewer components in the system, it's inherently more reliable, and also simply through improved redundancy strategies within the systems. Also, structural software improvements. By that I mean increased modularity and such, and then additional features also that provide us ways to build more or highly available services on top of the IP infrastructure. So integrating better with the layer 1 and layer 2 protocols, and also with the IP routing protocols, more features and functions. Again, we'll talk about that some more in the question and answer. But it isn't just about products and the boxes you build. Another thing that's really matured a lot is how we run our networks. The tools to run the networks have gotten at least a little better in the last 10 or 15 or 20 years, but certainly the processes have improved quite a bit. When we were running the networks 15 or 20 years ago, we were all pretty much amateurs at running networks. But I think this is an area where we've learned a lot from the telco guys in how to improve our processes in running networks. But at the same time, we've also really had to take those the telco approaches to a circuit switch view of the world and try to figure out how to apply those to a packet world. And that's really been one of the challenges, I think, in understanding how to build reliable, available services. But I think it is an area where we've really gained a lot of understanding in the last few years. So, with regard to growth within the POP and handling expansion and such, there will be more traffic. I think that's been the rule, constant rule, despite all of the claims of .com implosion and all these things. Obviously, there's still a lot more traffic. It's still growing, and so we need to continue to scale up the network to accommodate that. And maybe I'll disagree with Dave a little bit. I'm not sure. I think you were talking pretty much about memory bandwidth. That at least what we see is more or less, doubling of traffic growth every year. So at least we're more or less in line with Moore's law, roughly. And there are certainly some areas, like you said, memory bandwidth and things like that, where it might come out of line at different points in time, just like when we saw the big burst in number of routes in 95, 96 when the network became commercialized. So anyway, I think long-term some of this stuff aligns itself pretty well. And if it doesn't, obviously we can't just say this problem is too hard, walk away. So we'll need to figure out something. And so anyway, I think we're okay with core routers keeping up, in particular with the approaches that have been are coming to market now with multi-chassis devices within a single routing system. We'll be able to keep up with the scaling needs within a POP and within the network. So Dave touched on this a little bit too. We're really OC192 is the sweet spot here. One of the interesting phenomena that we've seen just recently, or kind of accompanying that. Something happened here. Weird echo. Yeah. Yeah. There's only one mic here now, though, right? Anyway, whoa. Okay, so before we always had the option where we were upgrading from T1 to T3 or T3 to OC3 or OC3 to OC48 or whatever it was. Basically, we were always taking up more space on the same fiber, but now with, as Dave alluded to, the OC192 is kind of mapping onto that fiber, and we're not taking a bigger channel of something else's bandwidth. We pretty much are the bandwidth on the fiber. So anyway, there's more OC192s there. It just doesn't there were more lambdas. It just doesn't work very well for OC768. So unlike what the trends we've seen in the past, where every couple of years we see this cycle again that Dave talked about, of kind of what I call a sparse build out of a given technology, and then we see a dense build out of that same technology, then leaping into a sparse build out of the next technology at each level. In this case, it looks like OC192 is probably going to hang around a while. So one of the things we're going to really need to figure out how to do well is handling parallel links in the network, because you'll see lots and lots of 10 gig going in parallel, and also improving our interaction with the optical core and how we manage those links as the IP network maps really more directly onto the physical fiber network that's available to us. Another topic that was on the list is handling. How do we do improving packet handling, and how does that interact with services in the core of the network? And so really that question, I think, is driven by the question of how long can we keep doing electronic packet switching in the core. And as I mentioned a couple slides ago, I think that we're able to keep up pretty well for at least the intermediate term future, the next 9 to 12 to 18, 24 months. And a lot of the really tricky packet handling stuff, some people say really ugly stuff, it's also maybe the most interesting things in some cases, because that's what allows us to run the voice over IP or the collapsing other data networks over our IP networks. So most of that's happening around the edge anyway, and so it doesn't really need to happen at 40 gigabits per second on a single interface. But that said, we do need to touch packets in the core quite a bit, and Dave alluded to this too. need to count them and filter them, need to protect ourselves against denial of service attacks, and sometimes do some packet scheduling. We need to do multicast replication, and I don't know, I don't see Greg back there. I know he would be angry if I didn't mention multicast, so I had to put that in. And this stuff pretty much all works at 10 gigabits per second now, so I think we're, again, okay there. Return on investment was one of the topics that came up in the panel, and I thought this was kind of interesting because historically we haven't, again, 15 years ago we didn't really talk about return on investment in NANOG because we just collected checks from NSF and spent the money. So life has changed, obviously. And so I'd say that the two things that are coming into play here and where Juniper is really focused is, one is providing a core that's scalable enough so you can depreciate that for a longer period of time in your network and actually see some return on your investment without having to replace it as regularly, and also provide the mechanisms for the core to collapse multiple services onto that core, fill the network, and collect more revenue and hopefully more profitable revenue off that shared core. And so I hope I made it in 10 minutes, I'm not sure, but it's not really a long time to talk about all this stuff, so hopefully we'll have some good questions and answers afterward, and that's all I have. Oh, Dave, we'll go to PDF.
Great. Thanks a lot, Dave. Great. Eric Brendel's he's actually, he replaced Kerry Parker from Chiaro Networks, and we're going to do his now, so let me pull that up. And here's Eric. Sure.
Morning. Again, my name's Eric Brendel. I work for Chiaro Networks. Today, in the 10 minutes that allotted to me, I was going to speak about router partitions. In general, what we see is, in the future, we're going to see maybe some large-scale deployments of, multi-chassis systems. So what makes sense is to have, some way to be able to divide up these large-scale systems into maybe multiple routers. So to structure my talk, I'll first talk about maybe some trends that we see in the industry and large providers. Move into maybe a description of router partitions, and then go through some applications of it. Okay, so what are we seeing in providers today? We're seeing, and a lot of these are driven by the economy. We're seeing some mergers going on. So what's the result of some mergers? We have some large providers that are purchasing other networks. So you have companies that have two networks that pretty much do the same thing. So there's a certain drive to integrate these networks. Another drive is a lot of large providers that have multiple backbones. They have an ATM backbone, they have a VPN backbone, they have a frame relay backbone. We've talked about this before as far as integrating all these services on a single IP backbone or a single ATM backbone. But maybe now, with the way the economy is, maybe now's the time that it'll really happen. There's also issues within the POP. A lot of providers, the POP has they've introduced a lot of equipment into the POPs through the years. They've increased the number of layers within the POPs to get more fan out to attach access devices. Also, they've added routers to increase the capacity of the POP. So another goal is to simplify the POP, reduce the interconnection, and collapse the layers. Multi-service networking. What does this require of equipment? What do we see? Well, one thing we see is that maybe SLAs will be more important. So this is more along the lines of maybe within the company that has an ATM backbone and an IP backbone, and they want to integrate these things. The ATM people might not trust the IP people to carry their traffic. They don't trust the reliability of the IP network or the quality of service that it'll give. So what we're seeing is more quality of service and high availability becomes more important. Things like protection and restoration, fast reroute, those things are becoming more of an issue. The other thing is the underlying transport facilities that are out there, they're not always necessarily protected anymore. So, what you can also do is bring protection up to an IP layer and have that as being the integrating force that provides all the protection and restoration. And the other thing is there's line rate encapsulation and tunneling technologies, whether it's MPLS or IP tunnels. These are some of the other tools that'll help integrate all these services together. The other thing is internet traffic is still growing. Providers are still seeing a rapid increase, so they're stuck in a position now where they have this growing traffic, but they're still being driven to cut costs. And the trends mentioned above, the consolidations of networks and services, that's only concentrating more traffic onto fewer network devices. So what all this spells out is that large-scale routers will still be needed, and probably we'll start seeing multi-chassis systems. Okay, so what is a router partition? It's basically virtual routers, and the difference between the router partitions and virtual routers is mainly the application of them. So the way the application of virtual routers is more for the core, and the way I look at virtual applications of partitions is for the core. The applications of virtual routers are more as a service to customers, and I look at that more as like an edge functionality, but they're really the same thing. If you're going to be partitioning your router in the core, I would imagine that you probably wouldn't need that many partitions. And within each partition is dedicated its own memory space, its own, processes run separately. You can run your separate routing protocols. You can even run different versions of your routing protocols. One important feature of routing partitions is cut-through routing. So if you have a large-scale router and you want to partition the router up into multiple routers, you don't want to waste two interfaces to connect two virtual routers. You don't want to physically have to route it out. So cut-through routing what that basically is it's a virtual link internally within the router, so that routing exchanges can occur between the two routers. And when a packet comes in on an interface, you do a lookup once, and it would resolve the multiple hops through the virtual routers. Another important thing about routing partitions is whether you have a single or multi-partition interface. So the capability to put an interface into multiple routing partitions is an interesting feature. So I'll start going through maybe some quick applications. And initially, a lot of these applications are just kind of like brainstorming ideas of things that you might want to do with partitions. The goal is, to provide an operational tool so that you can migrate your networks and integrate services more easily. So in this picture, we show two large routers, maybe in two different POPs. And the goal here is you want to integrate your networks and your services. So and this might be an intermediate step, and it might not be the ultimate goal, but the idea is each of these you partition your router into your different services. So your APM edge nodes could feed into the same equipment that your MPLS VPN routes or edge equipment feeds into, and same with the IP. So the benefit here is you have a single equipment that's working in the core for the core router. So if you want to, you can just purchase another shelf with excuse me, more interfaces. And you can flexibly choose which routing partition you want to put these interfaces in. In this example, each of these partitions, they operate over a separate backbone, so you have, each of them has their own IGP. Each partition is separated, so failures in one partition won't affect or like routing protocol software failures in one partition won't affect won't affect the other partition. You can run different versions of the software in different partitions. So if one network's you're using ISIS and the other one's OSPF, that's fine. Different features in one, different features in the other. If you have putting your internet routes in one partition, you're brave enough to deploy the MPLS BGP VPNs, you can keep all that stuff in a separate partition. Your APM folks, maybe they'll be a little happier because they know that their partition isn't involved with any of the BGP routes and scalability issues with that. So a next step in integrating services might be to combine all these wide area links and put it on a single backbone link, and that allows service providers to cut costs further by just operating a single wide area network. So what's required here is some sort of technique to encapsulate or multiplex and demultiplex these different virtual links. So your partitions in one POP would talk directly to the partitions in the other POP, and they can run their own IGPs and routing protocols across them. The other thing this allows you to do is, gives you a software sandbox. So you can create a partition, load a new version of a code that you want to do, and you want to actually test it out in the network before, and you establish your encapsulated exchanges, and then you can gradually migrate interfaces from one partition to the other. So what this gives you is it gives you a way to gracefully introduce new features. And basically the idea is that this is a new tool for migrations. And then maybe the next step is to deploy another partition that maybe does all your traffic engineering. And then what this does is this takes advantage of cut-through routing. So you have some coordinated traffic engineering partition where it can integrate all these services on the single backbone, so you can manage the resources more effectively on the backbone. So in this case, you only have one IGP going across your backbone, but there also are other options. When you provision LSPs, you can have them either terminate onto individual partitions, or they can come straight through. So you can have routing exchanges between partitions, or just between the traffic engineering partition and the service partitions. And again, the ATM people, they might be more keen to integrate their network with the IP folks if there is like no BGP in the ATM/traffic engineering parts. Another use for partitions is for the POP. Again, another trend was simplifying the POP. So in this example, what POPs traditionally they have multiple function equipment that has different configurations and different functions. And the goal is to reduce this equipment. So you can imagine if you have a large multi-chassis system, and you want to add a shelf, this shelf that has a bunch of ports, you might want to, you could create another router just by adding another shelf. What this does is it reduces a lot of the interconnection between these parts. And one strong part of this is with cut-through routing. With cut-through routing, you're not limited by the bandwidth between, say, traffic traveling between a backbone partition and a peering partition. And again, you separate your functionality, so your peering partition could run a different configuration, has different protocols running. So if you want to upgrade your software because there's new features in a particular BGP code, you might want to only upgrade the peering partition. So with all this, if we're going to be deploying multi-chassis large router, we're going to have a situation where we have a larger router, it's carrying more traffic, it's carrying traffic from multiple networks. There needs to be a highly available system design in order to support this stuff. And what highly available means is the system needs to provide equipment protection. So what that means is for all the cards in the switch fabric cards, the interconnection, the port cards, you need to have no single point of failure. And this could be either, you could protect your equipment with hot standby 1+1, or you can do something that's more cost effective, one for N. The other important thing is an in-service upgrade. So when your control plane fails over to another control plane, it's important that two things is important, that traffic is still transiting the router, and that your routing flaps aren't propagated through the network. So the other thing, there's a bunch of nonstop forwarding solutions out there. What's important with the nonstop forwarding solution is that you want to minimize the time that you're forwarding on stale information. So the topology changes occur in the network, and you want to make sure that time is reduced. around 30 milliseconds or 30 seconds. And you want that to be a deterministic time. You don't want it to vary based on the type of import policies you have and export policies. You also want a solution that's interoperable. And the other thing is you want a solution that if the router does lose its forwarding capability, the other router will be able to detect that. The last thing with high availability is the switch architecture. Complicated switch architectures generally, they have more problems with them. So simple switch architectures generally lead to a better, more highly available system. So in summary, the internet's still growing, and large core routers seems to be still needed. And with routing partitions, this provides an operational tool to be able to maintain your operational boundaries. If you have a POP and you have certain functions for certain routers, you can consolidate that all into one multi-chassis system while still keeping your operational boundaries. It's also a very useful tool for integrating networks, either as a temporary thing to get to your final architecture, or whether that ends up being your final architecture. It's also useful for new service introduction. And the other important thing is high availability.
Thanks, Eric. All right. Ori from Charlotte's Web Networks is coming up. If I could find this full screen. Here we go.
Okay, I guess I'll be one of the slow speakers because I hope you're not too tired of virtual router architectures. Basically, I will speak about the same concept we just heard. Maybe I will add a few things. Maybe we'll just hear more of the same. So what is a virtual router? Basically, it's a single system with several routers. I'm not mentioning whether it's one chassis or several chassis. It probably makes more sense in a multi-chassis environment. I'm not mentioning whether it's on the control plane or maybe it's moving functionality to the interface cards. Everything can be done. It's all a matter of technology. The concept is several routers, several logical routers living together on one system. What's the idea behind it? The idea is basically come to a POP, for instance, and replace most of the routers over there. Okay, a core router will never be able to change the place of an access router, but probably to change the place of the core routers, the aggregation routers, and maybe some of the edge routers which has functionality which a core router or a core router with a lot of functionality can support. It should be done seamlessly, which means basically you can take the same configuration you had on your routers on the POP and move them to the new logical or virtual routers on your system, and it should be co-located, of course. The co-location is important because, of course, the system has to be in one place, basically, and the distance between the chassis in the co-location, again, is a matter of technology. Okay, there's optical connections, there are electrical connections, there are all sorts of connections, and this is the factor that will affect the distance between the chassis or the virtual routers in your system. Virtual routers, of course, share common components, switching fabric, power supply, fans, everything which is a common component in a router. Though these components in all routers today are redundant, and of course in a multi-chassis system this becomes less of an issue. Again, redundancy is an important factor, especially when you're talking about these sort of magnitudes. A multi-chassis system can be very big, as you can imagine, and of course all this technology we're talking about is future technology. So basically most of the pipes over there will be 40 gig, 10 gig, very big line card capacities, which means redundancy and high availability of this sort of routers has to be 5.9, has to be, because one of these routers failing, you don't want to see the mailing list on NANOG after that. Okay, separate routing on control planes. That's the obvious thing. Virtual routers, the obvious thing it has to do is have separate logical being. Okay, whether it's running its own routing protocols, whether it's having its own interfaces. Again, the concept just mentioned by my previous colleague about sharing interfaces between virtual routers is a very nice concept, but it is a technology obstacle which will be solved. But again, this is one of the technology solutions we're talking about, and each vendor will probably solve them some way. As I said earlier, the increased relevance in multi-chassis system is obvious. This sort of solution can be done in edge, as most of you are familiar with, but the solution we're talking about now is basically taking separate processors, whether it's on the line card or on the routing engine, and running virtual routers. This sort of thing has more logic in multi-chassis systems. The idea also is not to make the router more complicated. Okay, the router has to remain simple to continue doing its basic functionality, whether it's in the core with the BGP performance, where the BGP performance is much more important, and the large pipe, or whether it's in the edge where you want to have it do the IGP convergence much faster and has smaller and much larger number of interfaces. So this is like a very simple, common POP architecture with the dual router architecture and everything. The simple example is just collapsing the aggregator routers and the core routers into one, and basically creating new interfaces between them, just because now it's interfaces connecting two virtual routers and not interfaces connecting between four separate routers. As you can also see, the two interfaces between the routers are now disappeared, and that's, as my colleague just mentioned, the cut-through routing you can, of course, do. This can be further collapsed into one router. Again, each network operator will have its own considerations, whether he wants to abandon the dual router concept, which, from my personal knowledge, won't happen in the next couple of years, just so everybody will be assured that 5 nines can really be achieved with routers. Okay, let's talk a little about pros and cons of the virtual router concept. Basically, it preserves classic configuration. If you had, I don't know, 4 routers in your POP, one of them is doing, 2 of them are doing core, 2 of them are doing aggregation, then you can use the same configuration you had, run them as a virtual router in a multi-chassis environment, and simplify a lot of things and save a lot of money. Maintains previous function in the POP basically means, as I explained earlier, if your core router previously you had was very simple router that has to do BGP very well and has a small number of interfaces, but each of them was a very fast interface, that will continue to be its function. Whether you have an aggregation router or an edge router which has had a very good IGP convergence and handled several or multiple interfaces very well, that will continue to be its task in the new architecture. Reducing the number of network elements is simple. Basically, as you can see, you're collapsing several routers into one, creating a multi-chassis system, which basically reduces the number of elements and simplifies your network. Nearly as robust as separate routers. Okay, this can be a pro and a con, I guess. As I mentioned earlier, you have common components or shared components. So basically, if you have multiple failure scenario, things can happen which can affect more than one router, and that's something you want to avoid. Again, you don't want to make this architecture affect the network more than it does. and that's why you will try to limit the number of shared components. Again, from the software point of view, the robustness remains the same. Routing protocols and performance of the routing engine remains the same. Let's talk a little about OpEx and CapEx, which is kind of a trend these days. Common components, of course. This means, okay, you reduce your robustness a bit, but you lower the price you have to spend, for instance, on switching fabric cards. Again, this is not such an issue when you're talking about multi-chassis systems. Intra-pop connections, of course, which can come up to a lot of money, especially nowadays where OC192s are not enough anymore, and you need 3 and 4 and 5 OC192s connecting your aggregator routers and your core routers and inside the core. So intra-pop connections are very, very expensive, and they don't give you any money back, or they don't revenue any money back. Smoother aggregated curve. Okay, that's a very nice option because you have a multi-chassis system. You don't have to buy a new chassis every time you run out of slots for your cards. Okay, all the cards in your system share. Basically, each of them can control each of the line cards in the system. So basically, if you want to upgrade your system by one card, you can buy a chassis, okay, but then anytime you need to upgrade one of your virtual routers on in the system, you can just add a card until you fill up a chassis, and then you can fill up the next chassis. You don't have to buy a new chassis every time one of the virtual routers finish its slot capacity. And the N+1 instead of the 1+1 redundancy, this is something we're all hoping will come of age. The 1+1 redundancy is certainly too expensive, even though as a router vendor, it works for my better money or better revenue. Cons. So as I said, common components fell together. This is something that should be considered, but in a multi-chassis system, and when you consider no single pole failure, this is something that should be solved. It's not such a big issue. It's only applicable for co-located routers. As I said, there is a limited distance between the routers in the system. And currently, there is only a single vendor for the entire system. Maybe there will be some standard along the way that can help all these currently proprietary technologies become something of a standard. So my summary, basically, that virtual router technology provide distinct advantages by, of course, lowering your costs, improving design of your next generation POP and core network. It is an alternative for reliability, as we mentioned. It will simplify your network topology because it reduces the number of nodes you have in the network. And of course, it will add flexibility to your co-location because, as I said, you can have multiple chassis in distance one from another, but still have them operate as one router. That's it.
Thank you, Ori. All right, Puneet from Flores is going to talk now. So.
I think the theme is pretty much similar, but let me...
No.
So if you take a look at the current POPs, you got too many routers. You got much of legacy equipment and redeployed gear. Things that used to be your core routers get moved more towards the edges. And then that basically means that more routers means more difficult to manage. Then you have your core routers. If you want to scale that, what do you do to that? You do a forklift upgrade. Why? Because you cannot scale them because they're limited to a single chassis. So there is a trend towards multi-chassis system. Reliability and availability are not very common in today's routers. Yes, they stay up for a long time, but they're not really fault tolerant, if you will. And then as you need more services, as you want to add more services, you actually have to add more routers
which then again leads to more complexity, more difficult to manage. So what's the pop of the future? In our view, again, there has to be some kind of collapse among the various layers. You have the core and the WAN layer collapse, where you got these 4 out in the middle, they get collapsed into 2. And then also, some of the higher speed aggregation edges can also collapse into these routers. So this basically leads to smaller CapEx and smaller OpEx, because now you got single devices to manage or lesser devices to manage. As you add all this collapsing functionality into one router, you obviously need to scale beyond a single chassis. And that's where you have multi-chassis routers, as well as the fact that you don't need to forklift upgrade your core routers anymore. As a router becomes bigger, it needs to be more reliable. As you put more and more functionality into it, a single point of failure, like a core router, even though you have 2 of them, even a single one going down has a big impact on your network. So in summary, the pop of the future has to be made up of fewer, bigger, scalable, and reliable routers. So let me dive a little bit into the reliability concepts. So how do you make your network reliable? There are multiple ways of designing networks. You can design them using non-fault tolerant nodes. You can design them using trust me, I'll be back nodes. And then you can design them using true fault tolerant nodes. The true fault tolerant means that the failures, if and when they occur, they're invisible to outside the router. Any failure inside the router is invisible outside. So non-fault tolerant nodes, that's what we do today. You basically do mirroring, where you have the left and the right, and the right routers are essentially a mirror image of the left routers. And what does this lead to? It leads to underutilized resources, as well as increasing the CapEx and the OpEx. Then you have the trust me, I'll be back nodes. Well, the trust me, I'll be back nodes requires or assumes that your network is stable when the node goes down. You generally don't have any route updates at that time when the node went down. But the interesting part is, when do routers go down? They go down when you have a lot of stress put on them, i.e. a lot of protocol updates. That's a contradiction. So how do we resolve this contradiction? Well, if you step back and take a look at it, it becomes clear that trust me, I'll be back nodes are best used when you are doing things like software upgrades. It's a very controlled situation where you know things are not going down in your network because of some instability somewhere. And hence, it's at best an incremental step towards a true fault-tolerant node. So what are these truly fault-tolerant nodes? These are routers which are purpose-built from the ground up for fault tolerance, where every subsystem within the router, be it hardware, be it software, is fault tolerant. There is no single point of failure, and the faults are tolerated inside the router and it's not visible outside. Essentially, no downtime, no reconvergence, no packet loss. And in the end, happy customers, increased revenue, gross margins. That's all I have.
Thanks, Puneet. Okay, Riyad Hartani from Caspian Networks. Thanks. Good morning. I'm Riyad from Caspian Networks, and I'm going to be talking about next generation core router design and POP designs from a vendor's perspective. So in terms of agenda, I'll basically avoid talking about whether or not you need scalable or reliable routers, because that seems to be pretty obvious. So I'm going to be talking about scalability and what it really means to have scalability on different perspectives, the switching plane, forwarding plane, routing plane, and management plane. Then same for availability and redundancy, and say what that means and how one might achieve it on
switching, forwarding, control, and management. Then move on to like emerging services and the type of new requirements they put on router design. Then talk a bit about how to simplify and how this availability and scalability can help you, achieve like consolidation and simplifying POP designs. So in terms of scalability, the first component of it is the switching plane. So over the last few years or so, we've seen like the emergence of a number of switching architectures, from hypercube to hypertorus to multi-stage classes to multi-dimensional meshes, or a combination of all these. So you've got the trend there. It is like moving away from centralized switching architectures towards more distributed switching architectures. But one needs to go a bit beyond that and ask a number of questions. And these questions are, for example, what would be the initial cost of scaling? So what would be the smallest shelf and switching capacity, amount of switching capacity that you would have to put in a network to be able to scale later on? Then what would be the upper limit of scaling given the architecture you're choosing? Things like the amount of increase in switching capacity when traffic grows, and you want that to be as linear as possible, so you don't have to add a lot of switching capacity when you have a small increase in amount of traffic to be switched. Then things like investment protection. You want to have a shelf that you would put in a network that you would be able to keep when you go from like one generation of I/O speeds, let's say 10 gig, to another one, 40 gig, 2-3 years down the road. So you should be able to leverage what you've got over time and use it as efficiently as possible. That is the most important thing in terms of switching scale. Is not really the architecture you're picking, but basically the intelligence you would have to put in a switch or router to use the switching capacity as efficiently as possible. You should be able to know at any given time, given your architecture, what the switch capacity is and how to use it as efficiently and effectively as possible. And I would think that's probably the most important thing to have in terms of switching capacity scaling. In terms of forwarding scale, I think we'll see over the years the emergence of a number of services over IP and TLS backbones, and this would map to a number of other things like QoS reports, the type of flows you're carrying, the type of packets you're carrying, smaller voice packets, larger, let's say, jumbo frame packets, and one should be able to maintain fully linear characteristics when all these traffic characterization models evolve over time. So from a forwarding perspective, that's what one should aim to do. In terms of routing plane scalability, I think the expectation is that over time, the amount of control information to process will keep increasing. The amount of processing per bit of control traffic on average will keep increasing, and the expectation in terms of how fast you would want to do it will keep increasing as well. So to achieve that, it's not clear if just following Moore's law on a CPU side and following the 10-20% growth on memory bandwidth latency on the memory side would be sufficient enough. So one may want to move towards more distributed approaches, to scale all the routing plane, different protocols. So that's not an easy thing to do because, some of the aspects in routing are inherently centralized. For example, you need to have a whole look of your LSDP to know SPF, CSPF, or your whole BGP database to the BGP decision process. So one should take that into account in deciding how to scale, what to distribute, and how to distribute it, in terms of various routing protocols. And each of them has its own characteristics, so the approaches will be different for each protocol from the other one. Then to complement the routing plane scaling, one should also scale the management plane. As you grow your switch, you will start having more management information, like things like statistics and configuration data and so on. That will probably grow to some extent linearly with number of shelves you would be putting in a system. So to do that, you should be able to clearly grow the amount of both processing resources to process this management information and the storage resources to store all this information as well. So on the scaling side, I would say that, really to have a real scalability at the switch router level, one should be able to do it for the different planes. The switching, the forwarding, the routing, and the management. Then, same applies to the availability redundancy. I think in terms of switching availability, the intelligence I was talking about in terms of scaling and figuring out where the switching capacity is at any given time and use it as efficiently as possible is also required to figure out, when, as fast as possible, when failures happen within the switching fabric for whatever reason, And, based on that information, you detect fast and you react even faster. So to know where the switching capacity is allows you to put the traffic, dynamically, as fast as possible over this available capacity, and as such, have almost no loss of traffic at all. And when you have additional degradation, additional failures, for example, catastrophic failures, you should be able to have a sort of graceful degradation and start from zero loss and, progressively move towards a graceful degradation of switching resources. Then the other thing you would want to have is when you put your shelf in a system, when you start growing it, you should be able to make sure that you're growing seamlessly without any downtime or no packet loss. So same applies for forwarding plane availability. And in this case, again, you need to have the right mechanism in the switch to be able to detect fast, when failures happen, and to be able to react fast and react efficiently. And this mechanism should be fast and predictable as well, and you given loads of control traffic to handle. Then in terms of control plane availability, I would probably separate it in two different things. The first one is the expected events in which you're gonna be, let's say, having a software upgrade, and then the time in which you're doing it. And then you'd be having the unexpected events in which failures happen without you knowing about them. So I think for the first one, the hitless software upgrade, you have the flexibility of figuring out, when to migrate state and what state to migrate from active to standby and do it seamlessly without any help from your network. So that's something you could do. In terms of redundancy, you could probably use a superset of the mechanism that you're using for a software upgrade and apply them also for a sort of seamless redundancy under unexpected events. I can either do that or to some extent leverage, the graceful restart type mechanisms that are probably a good first step towards that goal, but probably not the ultimate state and not the ultimate goal in itself. Then you should be able to do things like allowing every process and every protocol, for example, to act to some extent independently from others, taking into account the dependencies for sure, but allows you to do redundancy at the protocol level and the hitless upgrade at the protocol level as well. So, and to do things like this, obviously you're going to have it designed very early stages in your router switch, because it's probably very difficult to add it later on. Then same applies to management plane. One have to make difference between the control plane and all the protocols for routing protocols and what is required to manage the switch and the router. And I think both of them need to be able to be redundant and to some extent decoupled, because they're doing different functions and they have different mechanisms to scale and to be redundant as well. Then talking next is the services, the emerging services, and what sort of requirements that would put on the core router design. So, once one starts to put different services like voice or TTM or ATM or frame or whatever, over MPLS IP networks, then these calls for different sorts of QoS models and different sorts of service differentiation. I think the key word there is to be able to have a design that gives you enough flexibility to differentiate at different levels of granularity, allows you to do things like qualitative as well as quantitative differentiation. And you need to have the right QoS models and QoS building blocks in terms of shaping, policing, scheduling, and so on in your switch to do that. Then another example, just pick an example out of this that I have here is security. And let's say DOS as the subset of that. So today, you won't know that you have the DOS attack until either have a problem or even router is dead, for example. So I think again, you're going to have designs that that's probably a bit more intelligent from the perspective of looking at more data and analyzing data more efficiently and trying to have a lot of more predictive type behavior than reactive type behavior on your switches routers. Then next is POP architectures. I think this whole scalability and reliability that I talked about a bit earlier, and the ultimate goal is basically to be able to consolidate a number of network elements within a POP into one network element or multiple network elements as well. So this applies to both horizontal consolidation, which you're having different boxes doing similar functions in a network, as well as vertical consolidation, in which you're having different boxes in a network doing different functions. And one should talk a bit about things like logical routers, for example, in the way my colleagues mentioned it before, which I will, differentiate from virtual routers the way we use it in the VPN, VR terminology, for example. So cluster routers, you have like different routers, different like cluster routers talking to each other over fabric links instead of like external links in the network. So all these things allow you to do sort of consolidation of various network elements in a network. Then the second type of consolidation is more between the packet layer and the optical layer, and I think this will take a bit more time to happen. In the early stages, it may be a very simple and very selective like interaction between the packet and optical network, sort of GMP layers type UNI or so on, and over time going to have a sort of consolidated control plane that allows to control both the packet and the optical. But that will take like 3 to 4 years or above to happen, I think. Then just to summarize, I think the key points I wanted to make here is really in terms of scalability. One should look at the 4 dimensions altogether: the switching plane, the forwarding plane, management, and control, to be able to aim to have a really scalable router. Same applies for availability and redundancy. And in terms of features and design and so on, I think flexibility is a keyword. Flexibility to have like new mechanisms to allow you to deliver new services, and flexibility while maintaining enough like simplicity in terms of how you deliver the services over time. Here we go. Thank you. Thank you.
All right. Thanks, Riyadh. All right. Okay, we have Scott next. And we're running behind. Scott, you have 2 minutes. Okay. All right. Hang on just. Shoot. No, I hope not. Okay, 1 moment, folks. Hey, there we go. Okay. 1 moment, we're there. All right. Okay, Scott Paretsky from Beach Systems. There we go.
Good morning, everyone. How are you doing? My name is Scott Paretsky. I'm the test manager at Avicii, so I'm not one of those pretty marketing types, as you probably have guessed by now. Before I start, I just wanted to thank my first grade teacher, Mrs. Gordon, for drilling into me the importance of following instructions. Danny made it very clear to us that for us to get through this on time, nobody could have more than 7 slides and nobody could have more than 10 minutes to speak. So you'll be happy to know I did follow instructions. All right, let's be honest with ourselves. If we're going to solve a problem, we need to get honest. So it's almost like Alcoholics Anonymous. We could call this Network Operators Anonymous. Let's admit to ourselves, I'll be honest, that the IP network is not as profitable and not as reliable as those other networks, and we don't like that. So that leads to my prophecy, because we are all hearing your message. No one is happy with the fact it's less reliable and less profitable. The vendors are hearing that. I think that is the number one prophecy, that is the number one market demand, is that the IP network is as reliable as the other networks. And that means the IP routers need to be as reliable as the other switches. So what does that mean? That means, I think very shortly, you're going to see operational costs reduced significantly. And that's going to be due to robust routers, routers that are achieving 6 nines of availability. Did I say 6 nines? Yeah, I said 6 nines. We'll have 5 nines by the end of this year and 6 nines by the end of next year. And that's because the network operators are demanding it. And right now you're sitting there saying, you know, that sounds awesome, but it sounds crazy. Well, I invite you to come to my presentation tomorrow at 3 o'clock, evaluating core routers for high availability. Well, I'll actually go into the details of how we're getting there. So what are the causes of our failures, and how do we solve them? Well, according to the University of Michigan, which I'm sure there are many people here who know and love the University of Michigan, all right, router operations are the cause of 36% of the downtime. Link failures is the cause of 32% of the downtime, and router failures only 23%. Now, a very knowledgeable person that I know, Danny McPherson, actually said to me, "This is wrong." He would give router failures more than 50% of this, but that only goes further to proving my point here. So what are the things we can do to solve these problems? Of course, for router operations, there's scalable architecture, hot swappable components, and in-service upgrades. For link failures, things like composite links, and then for the robust MPLS-TE, fast reroute and standby LSPs, and then, of course, routing convergence, which has become so important to all of us. And then for router failures, there's distributed architecture, carrier class enclosures for routers, distributed software, and route controller protection, which is hot standby or the IETF approach with graceful restart. So all that's going to happen, and I see over the next 18 months all of these getting addressed across the board. Router vendors are hearing you, and we are going to support these. So why does reliability matter in the first place? Why do we care about more highly available routers? Well, the first problem is because we're only getting 3 nines out of the routers in your network today, we need the redundant router to achieve a 5 nines network. That isn't done in any other network. That's not done in the voice network. That's not done in the ATM network. So you're not standing for it now in your IP network, and we're hearing that. More highly available routers will remove the need for the redundant router, and that in turn reduces costs. More highly available and scalable routers also allow for simplification of the POP by collapsing the POP. Costs are reduced. So what does all this mean? This means you are going to be able to reduce costs and have higher reliability at the same time. You're going to have 5 9 routers in your network that are going to allow you to improve your SLAs, and at the same time, that's going to reduce the cost of your network. Okay? That's all I have. Thank you.
Okay, so before we do this, actually, we were going to ask the panel members a couple of questions, or allow them to discuss their viewpoints on it. But are there any questions from the floor for any of the panel members on anything that's been discussed?
I have one that came in over the net. None of you are talking about logical routers, where a large system can be split into many routers in the same physical platform. Many of you are claiming that you'll be doing a single forwarding. This may be a separate issue, I'm not sure. Many of these vendors claim that they will be doing a single forwarding table lookup for incoming traffic that may traverse multiple logical routers, right? How will this impact convergence? Since I assume there will need to be some type of merge of the forwarding tables of the multiple routers.
Okay, so I did hear some stuff about logical routers, I think, so, but if anyone on the panel would like to respond to the question. Dave?
I think some of this is semantics, right? What do we call a virtual router? What do we call a logical router, et cetera? And there are obviously a bunch of different strategies to approach this problem at different points on the cost horizon versus and complexity, and how do we approach these? And I think we talked about some of those in terms of you're using end-to-one, one-to-end approach, or one-to-one approach of redundancy, et cetera. The part of the question sounded like it was relative to the
Forwarding tables.
Yeah, the forwarding tables, and kind of, first of all, there needs to be some discrimination of packet on the incoming interface. So at least determining which forwarding table to drop the packet into. So I think maybe that's what was being proposed, not necessarily that there's only one forwarding table for the entire box.
Did anyone else want to comment on that?
Yeah, I'll basically just, say something similar. To the logical route, you don't really necessarily have to have like merging of folding tables into one. There are other ways of doing it. As such, not really affecting the convergence, the routing to forwarding levels. Okay. Bill?
I'm going to direct this to the gentleman from Avicii primarily, since you made a point of discussing intellectual honesty. I think there's a discrepancy that you need to address between, on the one hand, talking about 6 nines of reliability, and on the other hand, your slides showing, 36% or whatever of failures being in the router. Your 100% pie there was the 100% of the, say, somewhere between 5 and 15% of the total, which is not operator error. So I think, talking about 6 nines of reliability is kind of feckless when, the vast majority of all of this is, people fat fingering things, people not understanding what they're doing, and that's just not going to change without user interface, vast user interface and usability improvements.
Can you guys hear me? Availability is separate from usability. If you were to count usability there, you would have to consider an actual operator action that brought the router down. And it's, of course, most imperative to test before it gets to you to ensure that some CLI action does not bring the router down. In fact, if you see that happening with your router, I'd have to say your router vendor is failing you. The other point to answer that is for router operations, I'd say the actual largest reason for downtime in operations is software upgrades. And I think you're going to see a lot of the stateful failover solutions that you see from vendors actually addressing inherently in-service software upgrades that will prevent that.
Can I just follow up on that a second, Danny?
Yeah, great.
Actually, I've been trying to understand this really since I've been at Sprint, really putting a lot of time into this. And basically what I find is that your number is way off. It's about 80% of all of the unplanned outages are due to people and process errors. So when you start looking at the kind of complexity you have to put into a box to get 5 nines, it kind of looks like almost, we all want better reliability, that's just not an issue, but I think the complexity trade-off is something that has to be looked at, because basically you've got this people and process issue, at least in the bigger carriers, that dominates the router outage time by, by a fact, well, it's 80%. So that's the number that I observe, not 30. Okay. Or 36, I think you have.
All right, I don't want to disagree with you with your numbers. What that does make me think is maybe we should get back with our friends at the University of Michigan to repeat the study again and get more involvement from network operators towards those numbers. So I'll take that as an action item.
Okay, thanks, Scott. Randy, go ahead.
Randy Bush. The first problem is that we get enough spam on mailing lists. Why did we get an hour and a half that could have been put on 2 foils? Secondly, if you want to cut the box count down and the content down, to take a look at something called the DAX.
Thank you, Randy.
Stephen Stewart. 2 comments. One, or I should say, Stephen Stewart and my router vendor is failing me, which is, of course, for those of you who know I'm at PAX, we don't have routers. The improvements that you need to make in OANM are collectively astounding, and I think that this kind of speaks to the comments that both Bill and Dave were making, that I'm sure that the teams of people that you have working on configuration languages are paragons of human interface, user interaction expertise, but the stuff that they're cranking out is crap. I will freely admit that there's a range of usability represented there on the stage, from usable to just more complex than words can even encompass. I would encourage you all to work together in a forum like perhaps the ITF, perhaps not, whatever it is that you all need to do to work together to develop an abstraction of a router that lets us write our tools to interact with routers once, because we have to rewrite our tools every time a new vendor comes along who has come up with the gee whiz bang new language for interacting and configuring and otherwise doing the OA and M stuff that we all need to do. I don't need another way to configure BGP. I don't need another way to express all the things about an interface that are possible. I'd like to rewrite my tools once to something like XML and have a standard DTD for a router, and have you stop inventing new languages to talk to them. My other point is I did not ask anyone for 6 nines. I'm not picking on anyone personally up there, but I did not ask you for 6 nines. I would be happy with fewer than that, and I would build my network out of multiple cheap boxes, which is how we took down the voice network, if you will, because they built, they put all of their eggs in the system robustness basket and built a 6 nines device that was monstrously expensive, and we small mammals ran around at their feet with our little tiny routers that cost a mere fraction of the price. To the extent that you are attempting to bring us back to the world of astoundingly robust devices, they're coming at a price. And I would rather pay half the cost for 6 cheap boxes than twice the cost for one enormous but remarkably robust box.
Have them at the same price.
I don't believe you.
So I'm not a marketing guy, I'm an engineer. Leave me your business card because we've never met and we'll speak.
Okay.
All right. Thanks, Stephen. Avi?
I guess, again, my comment, not to pick on anyone in particular, talking about how many nines you get, is I'll believe 5 nines when I get an SLA on a router, and every time it crashes, I get 25% of the cost back. And again, I really am not picking on anyone in particular. And I guess my question, which I guess I won't ask for answers on, but as the panel answers this question, I guess you can answer one of my burning questions about the whole graceful restart and stateful failover world, which is that I actually have a different view. In a lot of the networks that I've seen, routers sort of rotting their state of what's going on in memory and due to bad code have actually caused a lot of outages, whether it's 100% or 10%, it's a lot. And I'm not picking on Ceph in particular, and I'm not picking on any particular vendor. But my question is, given that a lot of, whether it's 5% or 50% of the crashes are because of bad code causing rot of what's going on inside the router, why is it thought to be a good idea to preserve potentially rotten state across, a reboot? Maybe it would make more sense to answer that when you answer this question, but that's one of my questions about achieving reliability this way. I'm not sure that's the way to go.
Okay, thanks. Last question, and then we'll go to this question.
Hi, I'm Mazdi Abbas, and this is for the gentleman from Avicii. I guess my question is, how is a super reliable router supposed to help us if convergence and route table growth and so many other things are creating real problems for us? The box doesn't matter if the network doesn't scale.
That's a great question. That absolutely matters, and that's something that's being addressed now. So for me to claim that as a prophecy for the future would be me trying to kid you. I mean, that's right now. The question we were supposed to answer was prophecies for the future. So that's the one I addressed.
Okay, so would anyone on the panel like to take a stab at this question? It's basically the comparison between nonstop forwarding mechanism either. and also try and address Avi's question in the context, if you will.
This is Puneet from Plurus. I think in my talk also I mentioned that graceful restart is effectively useful for things like software upgrade. Now, as far as real fault tolerance is concerned, yes, there's a concern that there's stale state, etc., what am I fault tolerating? But if you take a look at it, a lot of faults in the router are related to things like slow memory leaks. And the fact that you got a memory leak means that the active process is the one that's going to go down, not the backup. Backup is not incurring the same memory leaks. So in that sense, the fault tolerance really buys you a whole lot, where you can really trust it and it works.
Anyone else? Okay. Eric?
Hello? I look at both these solutions. I mean, they pretty much do the same thing. They have the same goals. So they obviously stateful. To me, when you try to protect the stateful failover, you're keeping everything within your box. So when you're comparing solutions like that, you have to look at things like standardization, interoperability, like things like what do you do on peering circuits if the other vendor has a different equipment. So, and another thing to consider is the scope. If there's a failover in a router, graceful restart. With graceful restart, it's going to affect a lot of routers within your networks. I mean, if you have a full IBGP mesh with all the other core routers, all these routers are going to be affected by it. The other thing is, again, the time that it takes to fail over. It does take a long time to exchange a full set of internet routes, and that period of time, you're forwarding based on stale information.
Anyone else? All right.
So in terms of graceful restart versus stateful resiliency, I think there are two different things here. I mean, the first one is for the hitless software upgrade, in which you know exactly when you want to do it. And in this case, I think you have the flexibility of knowing exactly, what state you want to migrate, what state is required to do the graceful upgrade on the other standby card. And in this context, you have a choice on when to migrate state and what state to migrate, and then I think you can do it without relying on help from the network at all. In terms of redundancy for failures, like for unexpected event, I think even this one has different considerations. I mean, you need to know to some extent, why the failure happened, and based on that, figure out what mechanism to use. And let's say if you have a hardware failure and you were keeping state on the standby, then something in this context you can use stateful approaches to be able to recover the state. If not, then you have to have mechanisms that are a bit more advanced in terms of making sure you don't synchronize information in real time on both active and standby, not to have the same problem on both. And I think there are ways of doing it, although I think graceful restart is an approach that would be okay in the interim, and till you get time to get to better approaches that do not rely on network help to achieve redundancy as well.
Okay, we ran over actually, and Susan's asked me to stop, so sorry, Dave. I apologize. But so that's it, and real quick, just like to thank Susan and the NANOG folks and Group Telecom and all the panel members, obviously, and Randy for his infinite wisdom. And that's it, so thank you very much.